The new RTL modeling construct in Verilog. I've been pickpacking up my office as Siemens is closing my location. This marks the longest I've ever spent in a single office in hopping 15 years. Constantly, I was in the same building earlier with another company, Oven, for an additional 2 years. I've got a box of stuff from previous job that I rarely unpack, but it happened to go through it and found the proceedings from what was to become the first DVCON in 1992. I doubt these proceedings exist anywhere in digital form. In the proceedings was a paper published about a new RTL coding construct I've added to Verilog before it came an IEEE standard. It eventually becomes known as an unblocking assignment. Before discarding it, I thought I'd scan it and share it here. After dealing with the wires and registers, this is the probably second most challenging topic for people learning Verilog. Note that this paper was published a year before any other tool beside Verilog XL had implemented the language. The terms Verilog XL simulator and Verilog language were interchangeable. This is also before the IEEE 1364 1995 LRM adopted the terms active region and MBA region for the event queues. As the program chair of the 35th DVCON, I invite you to read my paper from the inaugural DVCON. I would also be delighted to have you join me at DVCON in person from March 2 to 5, 2026 at the Santa Clara Hyatt Regency. New RTL modeling construct in Verilog. Abstract. New RTL modeling construct have been added to the Verilog hardware description language. Before these constructs existed, designers had difficulties modeling true RTL level descriptions. This paper presents several applications of the new Verilog RTL modeling construct. Higher-level modeling applications such as pipelines using the new construct are presented. Introduction. The Verilog Hardware Description Language (HDL) has recently been enhanced by the addition of new RTL register transfer logic modeling constructions. These enhancements represent a significant improvement in the ability to write higher-level RTL models in Verilog. The new RTL construct eliminates the ambiguities found in the previous versions of the Verilog HDL that occur in register assignment when writing to and reading from a register at the same clock edge. The new constructs provide ways to describe RTL assignments that span multiple clock cycles. The classic RTL simulation. There is no one particular definition of an RTL modeling style. Primarily, RTL models describe the synchronous transformation of the data from one set of registers to another. This is defined in the granularity no finer than a clock cycle. The only circumstance where one needs the absolute value of time is in the definition of external clocks. A classic RTL description lists the register assignment that need to occur on each clock edge as shown in Figure 1. Each line represents a synchronous transfer of data to the registers on the left-hand side of this operator. Figure 1. Assignment. Less than equal less than hyphen operator. And the flow diagram in figure 2 shows the two distinct processes for evaluating expressions and updating registers. The inner loop represents the fan-out settling within the current simulation time. A true unit delay simulator would not have the inner loop and must advance time before re-evaluating any registers. This is not a problem when modeling pure sequential logic. The outer loop represents the advance of the simulation time. This is typically the next clock edge or state transition in the described system. Figure 2, RTL simulation flow. However, most designs contain some combinational logic which cannot be easier modeled at the behavior level. Until the delay simulators are not always the desirable choice when simulating these mixed gate and behavior level models. Event-driven simulators can simulate mixed level models with realistic delays more efficiently than unit delay simulators. Event-driven simulation. Verilog XL, like most event-driven simulators, uses a zero-delay event queue. An event can be a change on the up of a gate or the execution of a procedure statement. Event execute one at a time, creating new events that get placed at the end of the queue. When the queue empties, the simulator advances time to next scheduled event. Figure 3 shows the flow diagram for an event-driven simulator. The major difference between the diagram and Figure 2 is that the evaluation and register update processes have been combined into a single event processing algorithm. Verilog XL combines the inner loop with its event processing algorithm, producing a very efficient simulator. Figure 3, event simulation flow. The register assignment statements are common events in an RTL model. The value of the registers receiving assignment changes as each statement executes, destroying the previous contents. One characteristic of event-driven simulators is that they do not always guarantee the order in which events execute. Subsequent statements must use the new value of the register since the old value is lost. It is not possible to predict whether a statement will be using the old or new value of register without enforcing some kind of explicit ordering. So, race conditions in simulation. The Verilog assignment in Figure 4 are an example of what can happen when executing multiple blocks of register assignments on the same clock edge. In the example, there are 3 concurrent blocks, each assigning a different register. The registers A and B are supposed to exchange value the next clock cycle when register swap is true, SWAP is true. Figure 4. The Verilog Excel simulation of the example in Figure 4 yields unpredictable result in the contents of register A and B. There is a way to know which of the 3 blocks of assignment would take place first when the clock edge event occurs. If a statement executed the order they appears, the first 2 blocks would use the old values of a swap from the previous clock cycle. Register A gets the old value of B, but B gets the new value of A, which leaves A unchanged. A different ordering leaves the value of B unchanged and the value of A set to the value of B. It is possible to remove the ambiguity in the previous example by inserting delays and adding additional signals. Figure 5 shows the previous example rewritten with a combination of technique to remove ambiguity. Now the register A and B swap in as intended because the temporary wires created. Also the value of a swap is used in the statement because of the delayed assignment. There are several problems associated with these workarounds. Their foremost is the added complexity to writing models, adding extra statement just to get the simulation to work. At the same time, the extra statement reduce the performance of simulation. Synthesis tools get confused and create a superfluous logic, typically extra storage devices. So the new assignment operator. A new RTL assignment operator addresses these problems by creating a mechanism to clearly define the event ordering in behavioral models. The RTL assign operator puts the register assignment into a separate event queue, the execute after zero delay event queue. Because this operator is non-blocking, succeeding statements execute without waiting for the previous assignment to complete. The syntax for the RTL assignment statement is described in Figure 6. The Figure 6 states the RHS right-hand side expression evaluated immediately along with any indices used in the registers when the statement executes. Their values are placed in an RTL queue shown in Figure 7. The registers in the RHS expression update after the zero delay event queue finishes. So any event created by the updated register are placed onto the next zero delay event queue. So Figure 7 enhanced RTL event flow diagram. Some examples of the statement using the new RTL assignment operator are shown in Figure 8. The last example in the Figure 8 demonstrates a solution for another problem with procedure assignment. The index value address is read at the same time as data, not when making the actual assignment to MEM. Figure 9 shows the example in Figure 4 rewritten by replacing the procedure assignment operators with a new RTL assignment operator. Regardless of the order in which these blocks execute, registers A and B swap correctly, and the first two blocks uses the old value of swap, so Verilog XL executes all the three blocks within the same zero delay event queue, and updates all of the registers in the RTL assignment queue. The transport delay. Because the RTL operator queues assignment to registers, multiple assignments to the same register can be scheduled at the same time. These characteristics make it possible to model the transport delay, which describes the behavior of the devices whose output changes faster than the inherent delay through the device. Without the new construct, the simulator may produce incorrect result. In the example in Figure 10, the RTL assignment operator to out 3 is compared with the blocking assignment operator to out 1 and a continuous assignment to out 2 and a combinational logic description. So the Figure 10 is transport delay. And the initial pulse at 300 on out 1 is longer than a pulse on out 3 because the simulator misses the change on a signal B. It's not until the time 350 that the simulator observe a change on a signal A and set out 120, and out 1 is missing the second pulse at the 650 because the simulator misses the change on the signal at their time 550. Out 2 has the correct first pulse but misses the second pulse. Multi-phase clocks. An event controller may be used to postpone an RTL assignment until after the event occurs. The event controller may be a delay or a change on a signal. The feature enhances the modeling of design using multi-phase clocks. The expression evaluates one clock edge and is assigned on another clock edge. In Figure 11, the register members now functions properly as a master-slave flip-flops. Figure 11, two-phase assignment. The RTL level pipeline description. The non-blocking features of the RTL assignments is useful when describe pipelines. Ordering the assignment in each stage of the pipeline so that it simulates correctly is necessary. Figure 12 is an example of a 16-bit pipeline shift and add multiplier. Keep in mind that assigned register's index is evaluated when the statements execute, not when making the assignment. Figure 12. Pipeline multiplier. High-level pipeline description. Another recent enhancement to the Verilog hardware description language is the ability to put a repeat count on an event controller. This is useful when describing operations that require multiple clock cycles to complete. This feature, combined with the transport delay functionality of the RTL assignment operator, provides a method of modeling pipelines at a higher level that was not formerly possible. The multipliers in Figure 12 can now be written in a single statement as shown in Figure 13. The Figure 13 high-level multiplier. Summary. This enhancement to the Verilog language let engineers clearly define RTL models without the need for unnecessary complexity. Engineers will be able to improve the performance of their simulations because this reduced complexity. Furthermore, this enhancement provides a higher level modeling capabilities to pipeline and multi-phase designs. So this enables engineers to focus on their design instead of the design of the simulator. Bibliography. Average. Okay, today I read this article or paper, New RTL Modeling Construct in Verilog, DVCON2026. Thank you for your time. See you next time.